Okay, good morning, guys. So let's continue our discussion on what was left in the last class. Well, in the last class, as you may have primarily seen that this chapter, in the beginning of this chapter, I introduced the system life cycle, and you guys who will be the future's information system developer will focus on the very first stage in system lifecycle, which is the startup stage. And within the startup stage, we focus on these 5 stages in system development lifecycle. Well, here we focus on the development because you guys will be working as the future system developers, right? So these 5 stages in system development lifecycle are system analysis, system design, system development, which have been which are the 3 stages that were discussed in the last class. So today, let's continue on the discussion of system implementation. So after the system has been successfully developed and tested, and after users have been trained, now it is ready to be actually implemented. Systems implementation comprises 3 steps. Data conversion, system conversion, and documentation. Well, first, data conversion. In preparation for system operation, the first step in the implementation process is data conversion. If the new information system is replacing an existing one, then the old system's data must be transferred over the new one. So this migration process can be non-trivial for large systems. But fortunately, virtually all computer systems can write data into ASIC, that is ASCII files, which can be easily imported into a relational database system. For manual systems, the most time-consuming process is inputting data into the computer-based system. It may be feasible to use scanners for documents and forms, but most data in like a accounting system, the journals, the ledgers would have been manually input into the tables in the relational system. After all operational data have been loaded into the new system, the next step is to convert to the new system. If the organization is converting from an old system to a new one, then there are a number of options regarding the process of switching from the old to new system. These system conversion options are distinct from the data conversion process outlined for the system implementation stage. The first system conversion option is sudden switch conversion. and it is also referred to as cold turkey conversion. Sudden switch implies that users stop using the old system and switch over to using nothing but the new one. Obviously, this conversion option can be traumatic for users accused to the old system. In the event of major deficiency in the new system, the organization is left with no backup system. Sudden switch conversion is a high-risk proposition which should be undertaken only if the system has rigorously tested and there is a high degree of certainty that the system will pass muster under real-world conditions. The second conversion option is called parallel conversion. As the name suggests, the old and new system are operated in parallel. That means all transaction data are input into both new and old system. Parallel conversion provides backup in case the new system is fraught with serious problems. On the other hand, entering data into two systems and operating with system is likely to cause confusion among users. Obviously, with experience using the new system and after any bugs have been worked out, the old system will be discontinued. The third conversion option is called phased-in conversion. Well, in this option, the new system is brought online one module at a time. The advantage of this approach is that problems encountered are isolated to the newly introduced model. On the other hand, interfaces need to be built between the new module and the remainder of the new system. And this approach is also likely to cause confusion among users. So each conversion approach has its advantage and drawbacks, and implementer must choose the method with the fewest drawback for a particular situation. Documentation. As with system design and development, all steps in the system implementation process should be documented. All programs should contain documentation within the program using command lines. System maintenance, the manual for the system maintenance should be developed, outlining how the programs can be modified. The manuals detailing users' interaction with the system should be created. Of course, as we discussed in the previous chapter, most DBMS have a data dictionary feature, and itself constitutes a wealth of documentation about the database system. Test results and modification made to programs to address problems identified during testing should also be documented. The documentation should also address the conversion process itself and any problems that were developed to automatically transfer data from the old to the new system. Now let's go to the last stage, system operations and maintenance. The last step involves turning the system over to users. The operation and maintenance stage of system development lifecycle is actually the bridge to the startup phase of the system lifecycle. The system is considered operational, but will inevitably require maintenance. The specific steps involved in this last stage are: first, system operations; second, maintenance; and last, post-implementation review. So let's go over them one by one. First, operation. Operation of system simply means that it is deployed in its operational environment and users begin to use the system. Assuming that the data and systems conversion steps have been completed, all users have been trained, they can now start using the new system. But as discussed in the next step, there will be a number of changes that will have to be made to the system. So that's why we need maintenance. After the system becomes operational, it is, as alluded to the startup stage, is usually a time of instability. The degree of instability varies as the function of the complexity of the system. In addition to that, it is also a function of the amount of testing that have been done and the extent of user trainings that have been performed. A well-tested system for which the users have been adequately trained and which is not overly complex should not be unstable for a long time. And on the other hand, an extremely complex system that has not been tested adequately, and when the users are not sufficiently trained, will likely be unstable for weeks or possibly months. So here, what exactly does this instability refer to? There are two corrective maintenance methods. First, corrective maintenance. Corrective maintenance must be performed to correct errors in the system's logic. No matter how well the system has been tested, some number of hidden errors will always exist. Some of the errors may simply be programming errors. Others may be due to inadequate or incorrect elicitation of requirements from users. Although users are consulted at various stages in the process, miscommunication between analysts and users is a common problem that will slow down the system development process. Yet other errors may be due to hardware and software incompatibility, especially for large and complex systems. You can appreciate that there are a number of problems that can never be foreseen or prevented. Corrective maintenance can also occur as a result of new requests from users. As they become familiar with the system, users are in a better position to articulate their needs. They may well request system features which analysts feel should have been raised during the laborious system analysis process. It is quite difficult for users to specify their requirements with great precision without saying and using a system in the real world. There are alternatives to the traditional system development lifecycle that attempt to overcome these problems of communication between the users and developers. After the system has been more stable, with the initial glitches ignored out, only routine maintenance would need to be performed. So such maintenance is referred to as perfective maintenance. It is aimed at fine-tuning the system to improve its performance. User sign-off is typically not obtained from the perform such routine maintenance because functionality of the system is not effective. So as you may imagine, users are unlikely to complain about faster response time, which is one of the intended results of perfective maintenance. Post-implementation review. The last step performed during the system operations and maintenance stage. There are two main objectives of the post-implementation review. First, to obtain feedback from users regarding whether the system is achieving its intended objectives. And second, whether any improvements can be made in the system development lifecycle. So the post-implementation review is aimed at getting both outcome and process. This stage needs feedback. The results of post-implementation review can be used to rate the performance of system analysts, programs, and other people involved in the system development lifecycle. So a key issue in evaluating the newly implemented system is the questions such as, are users satisfied by means of a questionnaire? User attitudes towards the new system are obtained, and these responses are analyzed to gauge the extent of the user's satisfaction with the system. Ideally, in evaluating the success or failure of a new system, top management would like to see measures such as the dollar amount of increased sales or the percentage of improved productivity. But as you can imagine, these indicators are extremely difficult to quantify and attribute solely to the new system. Given the difficulty in obtaining hard measures, user satisfaction often becomes a proxy for system success. If users are dissatisfied with the new system for whatever reason, it is likely that they will not use the system too much, and it must therefore be considered as a failure. If the new system is more complex and difficult to use than the one that it replaced, or if it simply doesn't provide useful and timely information, users will report being dissatisfied. So it is easy to say that user satisfaction can be a good proxy for the system success or failure. Critics of user satisfaction as a measure of system effectiveness point out that happy users are not necessarily productive and efficient. A system with pleasant graphics, sound effects, and quick response time may make users very satisfied, but still not be providing them with the right information at the right time. So it is crucial to design a user satisfaction questionnaire that goes beyond the mere appearance of the system and tasks, asks probing questions about the tasks that users perform and how the new system helps them perform those tasks. In addition to questionnaires, other methods of obtaining evidence about the success or failure of the system should be used. A system-generated statistics regarding usage and patterns of usage can be very valuable in determining whether the new system is achieving its intended objectives. In addition, simply observing the users perform tasks using the new system is also helpful to evaluate the system's success. As is apparent in the description of system development lifecycle, there are a number of steps involved in this process. Depending on the size of the system development project, and the number of people involved. It can take anywhere from a few weeks to several months or even several years to complete a project. At the initiation of the project, it is critical to list all tasks involved in each stage in the system development lifecycle process and estimate the time required for each task. Assigning system analysts and programmers to the projects is another important task that has to be performed. After project tasks have been identified and time estimates developed, a number of project management techniques can be used to control and monitor the system development lifecycle process. So here, in this chapter, two popular techniques will be briefly discussed. They are Purge Chart and Gantt Chart, which are two project management techniques that you will be studying in probably another course. But here we will have a brief discussion of these two techniques. First of all, the Gantt chart. This figure on the slide shows a relatively simple Purge chart of the steps involved in the system analysis. As shown in this slide, the Purge chart is a network diagram of all activities, listing activities in sequence from left to right. The duration of each activity here shows in weeks, the duration with an unit of weeks. It's shown in the parentness, successor, and preceders activities for each step can be identified. The resulting diagram shows first, it shows tasks that must be completed before others can begin. And second, the tasks that can be performed concurrently. Well, for example, this figure reveals that the system survey and feasibility analysis can be conducted concurrently. But both system survey and feasibility analysis must be completed before the process of creating ER and DFD diagram. There are two paths through this network. Step 1, 2, 4, 5 with a duration of 14 weeks and 1, 3, 4, 5 with a duration of 12 weeks. The most significant contribution of the Purge chart is the identification of the critical path through the network. The critical path is simply the longest path. through the network diagram. The reason it is considered as the critical path is that any delay in an activity along the critical path results in a delay in the completion of the entire project. For example, in this Purge chart, path 1, 2, 4, 5, which has the longest duration, 1, 2, 4, 5, is the critical path. Activities that are not on the critical path have slack time associated with them. These tasks can be delayed for a certain period of time without affecting the entire project's completion time. So, in this Purge chart, feasibility analysis can be delayed by 2 weeks. At most 2 weeks without affecting the project's completion time. A significant implication of the critical path is that the project duration can be shortened by allocating additional sources to the activities that are on the critical path. But one drawback of the Purge chart is that it cannot show the extent of completion of each activity. So another project management technique is the Gantt chart. In the Gantt chart, activities are listed on the left with a timeline shown across the top of Gantt chart. Horizontal bars are drawn in the body of the chart to depict the starting and ending points of each activity. The length of bar indicates the duration of the activity. Initially, each bar is hollow, but as the work is completed on each activity, the bar for that activity is shaded to show the extent of completion of that activity. So, Gantt chart shows the status of the entire project at a glance. But unlike the Purge chart, Gantt chart doesn't show predecessor and successor activities for any given activity. Well, actually, these two popular tools for constructing Gantt charts are the two software. Microsoft's Projects and Project Libre, which is an open source alternative of Microsoft Projects. Well, if any of you is interested, you can download and install these two softwares to explore how Purge chart and Gantt chart are developed. So this figure on the slide shows an example of Gantt chart created using Microsoft's projects. This chart shows the sequence of steps involved in a software development. All right. That's all we want to discuss in system development lifecycle. So all these 5 steps have been discussed: system analysis, system design, system development, system implementation, system operation, and maintenance. So in the next chapter, we will focus on the logical design of the system. We will focus on the EER, and DFD diagram development. So that's all for this chapter. And please let me know if you have any questions before I leave. Any questions? No? All right, so that's all for this chapter. I will see you on Wednesday morning, this Wednesday morning. And in the next class, we will start the new chapter to discuss the logical design for the system development. All right, bye-bye. See you guys.